Yeah, so that's a great connection to the next speaker and to the next presentation, which is quantifying aleatoric and epistemic uncertainty machine learning, and are the conditional entropy and mutual information appropriate measures. So the talk will be given by Lisa Wimmer, and this is joint work with Yusuf and Paul Hofman, Bernd, Bischl, and Eyke Hüllermeier. Okay, please.
Okay. Hi, everyone. Can you hear me well? Hi. So my name is Lisa. I'm with the LMU in Munich, and I think I just even got the best introduction I could ever have. So thanks so much. This is actually my very first time at a conference, so this is all pretty exciting. All right, so as we just said, I'll be speaking very related to Yusuf's talk about measures that we can use to quantify aleatoric and epistemic uncertainty in machine learning. And while these measures have been around for so long that we might have come to taking them for granted, I hope I can convince you that these are maybe not so well behaved as we might like to think. So let's take just a briefly a couple of seconds to get on the same page here. So when I'm speaking about uncertainty in machine learning, I will always be speaking about predictive uncertainty. As we have just heard, it is common to assume that uncertainty can arise from two different sources. So the one are the data themselves. Whenever we have such things as measurement error or simply finite measurement precision, we will have uncertainty that arises from imperfect data. So this is the aleatoric part. Whereas, on the other hand, we have uncertainty relating to what we as researchers might lack in knowledge about the data generating process, or maybe have in wrong assumptions. So this is the epistemic component. There's also one implicit assumption we are making here with our paper, namely that our hypothesis space here is rich enough to contain the true hypothesis. So some hypothesis F that is just a functional mapping from some input space to a label space, and we have a ground truth mapping F star here. And we assume that if we can accumulate enough knowledge, for example, by observing enough samples, then we can shrink the feasible hypothesis space to just come down to this one ground truth hypothesis. And now what we're interested in is to somehow quantify the total uncertainty about our prediction and hopefully disaggregate that into its aleatoric and epistemic components. And I've made that little question mark about the equal sign here because the additivity of this relationship is actually something we would like to call into question. Before we can quantify uncertainty, we first have to briefly think about how we can represent uncertainty. And we would argue that we need at least 3 different levels if we want to have aleatoric and epistemic uncertainty as quantifiable objects. So on the first level or the 0th level, we actually don't observe any uncertainty. That is just the labels from our label space that we can observe in practice. So for example, in a binary classification problem, we could observe positive or negative labels. So you might, for example, think about a little example where we draw data or have a random number generator, draw some figure, just some number, which could be either positive or negative. We would like to quantify the probability that the next number this random number generator generates is positive or negative. So on some level 1, we get a conditional distribution, the one that we're actually trying to estimate with our model here, of y given x. So given some input features, whatever these might be in this case, that tells us something about the probability of this next number here being positive or negative. We have a ground truth theta asterisk here, which tells us that, okay, probably this thing is biased in some way that it tends to generate negative numbers. And also our estimate of that, which is theta hat, points in the same direction. However, there's some gap. But as you can see, this is not an either or thing. This is not either 0 or 1, but it is a probability. So we automatically can quantify some uncertainty about that. The closer this is to 0.5, the greater our uncertainty would typically be. And now for us to be able to also incorporate epistemic uncertainty, so our uncertainty related to the knowledge about the data generating process, we need something even one level higher up. And this could, for example, be a second order distribution. So this red distribution here tells us something about how certain are we that this y given x thing that we are estimating here might be something like 0.2 maybe, that this is actually the true ground truth. And the more the probability mass is spread between 0 and 1 here, the more uncertain we usually are. And here we seem to be fairly certain that this random number generator tends to generate negative examples. And the expected value of this red second order distribution is then exactly theta hat. So before we now think about these entropy-based measures, let's try to build some intuition as to how we actually would uncertainty measures to behave in a reasonable manner. So if you recall, we want to have somehow a quantification of total uncertainty and disaggregate that into aleatoric and epistemic uncertainty. So let's look at a little running example that you will see a few times more throughout the slides. We're considering a sequential learning process where we assume that we can accumulate knowledge over time, which is here just exemplified by the number of samples. And we would have some properties that we would like to hold in this case that seem somehow reasonable, and I hope you agree with me here. So the first thing is, in the moment of total ignorance, where we have seen 0 data, we should have maximum total uncertainty, and in particular, maximum epistemic uncertainty, because we have essentially no knowledge at all, right? So it can't get any worse than that. Also, we would like to see that the epistemic uncertainty reduces over time as we observe more samples and vanishes in the infinite limit of sample size. So this, if you recall, relates to that implicit assumption about the hypothesis space we made here, because we think if we can accumulate enough knowledge, then we can actually reduce our knowledge uncertainty to 0. For aleatoric uncertainty, on the other hand, this has nothing to do with our learning process at all, because this is just an inherent property of the data generating process and is not concerned with us learning about this process. So this one should be a constant throughout the learning process. Okay, so now we have settled that. Let's look at these measures that are so common in the machine learning literature that are actually originated in information theory. So these date back to Shannon entropy sometime in the 40s. What we are doing here, let's start with total uncertainty. How can we quantify that given a prediction? So we first take the expectation over a conditional distribution of our labels given some hypothesis data. So if you recall that little picture on the right, that is essentially just marginalizing over all the different hypothesis data that we could have and arrive at our prediction theta hat here. So this will be our marginal label distribution that we can predict. Now we take the entropy over this distribution and essentially quantify the uniformity of this thing, meaning that we think we are maximally uncertain if we deem all labels to be equally probable. And now by standard results from information theory, we can just decompose this Shannon entropy into 2 further quantities. The first one is the so-called conditional entropy, and we simply switch here the expectation functional with the entropy. So for each hypothesis between 0 and 1 in this case that we have, we will take the label distribution this hypothesis induces, quantify the entropy over that, and then take the expectation with respect to our second order distribution. So that is something like the average entropy that we could get. And now if we stipulate this additivity, that we say, okay, it is reasonable to assume that aleatoric uncertainty and epistemic uncertainty should add up, because presumably they come from 2 totally different sources that are kind of independent from each other. So it might be reasonable to have this additivity here. Then we end up with the residual quantity, which is just equal to the mutual information. And this can be taken to quantify the epistemic uncertainty. Because intuitively, we could think of that as the uncertainty reduction about our label distribution had we had the opportunity to observe the true distribution of theta. So that is kind of the idea here. But now let's think again about the fundamental relationship this induces if we take these quantities to measure our uncertainty. So we have, first and foremost, this additive relationship between conditional entropy and mutual information that then constitutes the Shannon entropy as our measure of total uncertainty. But now let's get back to our little picture here that we drew in the beginning with these assumptions that we made, which I hope you found as reasonable as I do. And we will quickly see that this is not really an additive relationship, right? So this orange curve depicting the epistemic uncertainty and the blue one, these don't add up to the black one. So that is kind of problematic. Because if we postulate total uncertainty and epistemic uncertainty to be maximal in the beginning of the learning process, but we also have this additional restriction that Shannon entropy and mutual information take their maximum at the same level because they're on the same scale, which is kept by the number of classes essentially. So they assume their initial value at the very same level in the beginning. So we can see that something does not really add up here. So either this assumption is not meaningful, or the aleatoric uncertainty cannot be a constant, or this additivity assumption breaks. So something's got to give. What we rather observe in practice then, if we stipulate this additivity assumption to hold true, is that we get something like an estimate of the ground truth aleatoric uncertainty that looks kind of like a lower bound. And the important thing for me here is that for you to realize that our estimate of aleatoric uncertainty must necessarily be compromised as soon as we have epistemic uncertainty. Because you can always also see that this dilemma kind of resolves the more we go into the direction of observing more samples and thus gaining more knowledge, right? But if our level of epistemic uncertainty is high, so we know very little about the data generating process, then our estimate of aleatoric uncertainty can somehow not be right. Okay, and the other thing which I think is really critical in this case is that it's essentially this regime of little or no knowledge that we are quite interested in to quantify uncertainty. Because if we have seen infinitely many data, uncertainty quantification is maybe not so important after all. So we thought maybe we should not just criticize measures, but also be constructive in some sense and come up with some more or less formal properties that we think a meaningful uncertainty measure should have. These are quite a lot, but I will showcase 2 of them with a little toy example. So for you to see that these also don't hold for the set of measures that we have just seen. We will consider this little toy example here, which is just essentially hypothetical level 2 distributions. So these Q distributions that we saw before. We can maybe revisit this example of the random number generator and think about, so this is basically our epistemic or second order belief about the probability of this random number generator of producing a positive or negative sample. In the top left case, this is just a uniform distribution. So we are absolutely unsure about the probability of this thing putting out a negative number. Whereas in the top right case, this is a mixture of 2 direct distributions. So we are absolutely sure this thing either always produces negative numbers or always produces positive numbers, which also means that as soon as we observe the next number drawn from this process, we know for absolutely sure the true probability of this thing. So then we said that we would expect that epistemic and total uncertainty should be maximal in the beginning of the learning process. So when we have 0 knowledge, and the next best thing we can get to expressing 0 knowledge in the world of probability distributions is the uniform distribution. So I think it's reasonable to assume that both of these quantities should be maximal if the Q distribution is a uniform distribution, where we have absolutely no idea about the true theta value. But if we look at the numbers here, that is very obviously not the case. But it is the case for the distribution on the right side, for this direct distribution. But I would argue that this does not represent full ignorance or 0 knowledge, right? Because we are very, very sure that this is either exactly 1 or exactly 0. So that led us to believe maybe that this mutual information as a measure for epistemic uncertainty is maybe not so much a measure of full ignorance, but maybe rather of conflict in our hypothesis. Because the conflict between the hypotheses is indeed maximal on the top right case. Okay, and the second thing to highlight here is that if we have 2 Q distributions that have essentially the same way of spreading out their mass or their probability mass, but they're just in different locations, then we would also expect that these 2 have the same epistemic uncertainty. So that is the example in the bottom row. We have 2 uniform distributions and the width of their support is exactly the same. They are just shifted by some amount. But here we can see that the epistemic uncertainty for the bottom right case is indeed not the same as for the bottom left case. Even if we were willing to accept that these 2 numbers should be different, I think it would be much more plausible for the epistemic uncertainty of the left case to be higher, because this one is closer to the 0.5 theta distribution that has basically maximum ignorance about this random number generator producing a positive or negative number. So clearly some things don't add up here, and we see some behaviors that strike me as quite inconsistent. Besides these toy examples, we also conducted some empirical evidence. I won't go into much detail here, but what we did was try to reproduce this running example that I showed you before, where we increased the number of samples over the learning process. And we did that considering a classification task. So this is CFAR 10, and we hit that with a deep ensemble. We can see what we have already suspected from our theoretical reasoning, that in particular in the beginning of the learning process, where the learner has seen only very few samples, these estimates of our measures seem to go rogue, essentially. So we definitely don't see the epistemic uncertainty starting at its maximum level. And also the aleatoric uncertainty in blue is definitely far away from assuming a constant value, right? Yeah, and also in different other experiments, we see all sorts of things that don't really add up. And this is always more pronounced in the parts where we have seen very little data, so we have less knowledge, and where we would actually like our uncertainty quantification to be especially meaningful. Okay, so let me resume our main criticism that we are making in this paper. So I hope I could make you see also that we think that the standard set of uncertainty measures rooted in information theory based on Shannon entropy is maybe not so appropriate as to quantifying predictive uncertainty, especially when we have limited knowledge. Concerning each of the individual components, the epistemic uncertainty behaves counterintuitively. We have seen that in some of the examples I showed. And we also hypothesized that this could maybe be just rather a measure of conflict than of ignorance, which might not be a bad thing in itself, but is something that, yeah, we should keep in mind when computing this uncertainty. As for the aleatoric uncertainty, here we have the problem that uncertainty propagates through from a higher level. So as soon as the epistemic uncertainty is present, which it always is basically, because if we didn't have any problems finding the true data generating process, then I guess we would all not be sitting here. So this is something we always have to deal with. And this will always inflict the measure we can have about the aleatoric uncertainty here. And lastly, for the total uncertainty, I have not talked about this before, but this is something that is also quite easy to see, I guess. We have seen that we arrived at this level 1 distribution theta by marginalizing out over our posterior belief or second order belief Q. And of course, marginalizing is always equal to a loss of information, right? Because as soon as two of these Q distributions have the same expected value, then it doesn't make any difference if they are spread out very widely or rather narrowly and peaked, because we always arrive at the same expected value, which will give us, by consequence, the same total uncertainty. This is also something I think might not be so desirable. And lastly, we saw that if we are willing to postulate some properties or some desiderata for our uncertainty measures, and we are in the regime of finite data or finite knowledge, then this additivity assumption cannot really hold. Or else we have to give up some of the other assumptions. So as soon as we have limited knowledge, we arrive at some contradiction or other here. So yeah, a way forward to end on some more positive note here, what can we do? So obviously, the best solution would be just to find a better set of measures. So I think it would be a good idea to go about this from a more rigorous way of thinking in terms of mathematical foundation. So maybe find some axiomatically justified measures that fulfill the properties that we would actually like to see. And also this is very important in my opinion. We should find something that takes into account this level 2 uncertainty on the epistemic part, trickling down into our level 1 and the aleatoric component. But maybe we must also pursue a more radical stance and even move beyond the measure or the world of probability measures in general and consider some framework that represent uncertainty in a more general manner. So that could be, for example, imprecise probabilities, possibility theory, and so on. So if you have a better idea, please come forward, visit me in the poster session afterwards. I would really like to hear if you have any suggestions for improvement. And I'm very happy to take questions.
Great, thank you very much. So before we take the question, we have discussion.
Yeah.
So.
I'm online.
Oh,
Hello.
online. Okay. Okay. So
Should I share screen or will you control the?
No, I will switch the slides.
Okay, perfect. Sounds great. So my name is Masha Ikina. I'm a research scientist at the Toyota Research Institute, or TRI. Next slide, please. Next slide, please. Thanks. So this paper is actually a really enjoyable read, so congratulations to the authors. My personal takeaways from the paper, which seem to align with most of what was just presented, were that aleatoric and epistemic uncertainty are approximated during the learning process, and so their decomposition into conditional entropy and mutual information may not behave as we would expect. The additive decomposition can be problematic when the approximated aleatoric and epistemic uncertainties are intertwined, as was just mentioned, during the learning process. What is maybe a little bit more of an extrapolation is that the underlying assumption of uncertainty estimation techniques that we have now is often a good learned model. So a model that performs really well in the training set and, is really good at figuring out what is in distribution. And that is not always the case, and we don't always know whether that's the case. And then the last point I had here for a takeaway is that a key issue with the current epistemic uncertainty measures is that they focus on information conflict rather than lack of information. And this is also pretty much the concluding point of the speaker as well. So that's great. Next slide, please. So some of the questions that sort of came to mind when reading through this paper, and some of these questions are also my own biased personal questions that I think about when looking at epistemic uncertainty estimation. Should we push towards learned uncertainty estimators like ensembles? And the paper actually looks at some empirical studies on CIFAR-10 and MNIST with ensembles. Or should we focus more on post hoc statistics, like techniques like conformal prediction, for example? Why, despite the small size of the ensemble that's practically used, do ensembling methods work so well in practice? The paper mentions that they're de facto standard, and that's definitely true, particularly when looking at learning in practical applications like robotics, which is the space that I come from. My third question is, would learnings from fields like evidential theory be useful here, as evidential theory can actually handle both lack of evidence as well as conflicting evidence separately? And my guess is the first talk from today, Creedal sets, can also similarly handle these ideas. So is that just the way to go with epistemic uncertainty? And then the last one is less of a question to the authors necessarily, but something that I think is important for the community to think about, whether these ideas scale, particularly beyond things like MNIST and CIFAR-10 and towards bigger data sets and more practical applications. How do the estimates that we have right now evolve and perform in those settings? Thank you.
Well, Masha, thank you. That was really a very good summary. I especially agree with the point on uncertainty quantification being only as really meaningful if we have models that can capture the underlying process well, because if we have models that predict poorly and are less calibrated, I think calibration is also the topic of the next two talks, then yeah, essentially I think what we're doing here is not meaningful at all. So thank you. And also for the quite good questions. I'll try to answer them as best I can. So pushing towards learned uncertainty estimators or post hoc statistics. I think both of these things like ensembles or conformal prediction perform very well in practice. However, like from my gut feeling, maybe I'm always one that likes to capture the whole of things. So inside, I'd also more argue for Bayesian statistics and being as exact as possible, because I think the posterior landscape, for example, is usually so very complicated that by using these crude approximation like deep ensembles or conformal prediction, we can never be quite sure which part of the posterior landscape in space we don't get to see. And if this is perhaps but the part that is essentially informative and important for safety critical application. So I would rather argue for finding or making exact inference more feasible. So that's the first point. For the second point, that is also quite interesting, and maybe something others have been worked on quite a lot, why ensemble methods work so well despite a small ensemble size. So I think that this is more related to stuff like regularization and also symmetries that we can usually find in the lost landscape of neural networks in particular, because it is well known by now that while these things are very multimodal and very complicated, we have a lot of symmetries in there. So there's parts of the lost landscape that just repeat over and over again. And we also have very broad valleys usually, especially if the thing is well regularized, where we have almost the same loss. So if we initialize some deep ensemble models in there, chances are that we can find different parts of the lost landscape and cover those with only a very small set of models. So while the landscape might look very complicated, the interesting parts might actually be very few. Learnings from evidential theory, I'm, to be honest, not too familiar with that, but also the senior researcher, Professor Hüllermeier, who was on the paper, is an advocate for things like that. So I think that would indeed be a very promising direction, and also something that people around Yusuf are looking into. So definitely yes. And for the last part, I'm not too sure. I've also mostly worked with these small machine learning data sets, but I think you really might be onto something here. And in particular, because there's also work on uncertainty quantification related to always using these very carefully curated data sets like MNIST or CFAR10 that are relatively simple to predict. And also, as I said, well curated. And you can also show that they tend to have very low intrinsic aleatoric uncertainty as compared to real life and real world data sets. So I think definitely the community should probably incorporate into their benchmarks also more or less well-behaved data sets to get to the point of things.